Hi, my name is Manish Gupta, and in this video, I'm going to talk about this interesting work called Refrag, which is basically an interesting way of doing RAG and in general decoding from a transformer-based decoder models using this compress, sense, and expand technique. Okay, the promise is like 31x faster decoding, 31 times faster decoding, right? So let's basically understand what is their main idea in this refrag model that makes it 31 times faster. Okay. So let's basically start with what are the major issues in retrieval augmented generation, right? So retrieval augmented generation oftentimes has long context input. So basically, let's say if you are retrieving for a given query 10 different documents, well, these 10 documents, if each of them is like 500 tokens, that comprise like 5,000 tokens worth of long context inputs, right? And that leads to higher latency in terms of inference and obviously more VRAM for key value caches because we have longer context. All of that basically needs to be retained. The key value caches have to be retained for all of those tokens, context tokens. Now, this also basically means that when doing generation, you end up with high time to first token, right? So time to first token basically means how much time does it take right from the beginning of the query to generate the first token. It also means higher time to iterative token. So then every next token after that, right? So in fact, time to first token, it's basically quadratic in terms of the input context size, and time to iterative token is like linear in terms of input size. Right? And it also means low throughput overall, right? So therefore, long context inputs in RAG are great so as to generate good quality answers, but also, they can lead to latency and throughput issues. However, an interesting insight that these guys found is that contextual passages are diverse. So when people are trying to do RAG, they obviously also try to do diversity in terms of the retrieved documents, and sometimes by just deduplication and sometimes by ensuring diversity so as to have orthogonal information that might be really important to answer the question. Right. So, which basically means that those documents typically have not much to do with each other, in which case people observe block diagonal attention patterns, which means that, that there is typically not much that one document can learn by having attention on tokens of the other document. Okay. So now this means, so that's basically an interesting observation, which is what is exploited in this refrag architecture. Uh, if you're just doing standard RAG, it has several of these issues. Inefficient token allocation. So basically, there could be like 10 documents which are retrieved, but only a few of them are important. There is also wasteful encoding and other information. So when you're doing RAG, it has a retriever and a generator, right? So a retriever basically takes the query, it matches with the document tokens or document embeddings and finds out relevant ones. Now, when it finds out relevant ones, typically the document text is used as it is in RAG. Why use a text? You could actually leverage those embeddings as it is because you've already done so much of inferencing and so much of computation. So there are those embeddings, there are those query document correlations that you used or that you basically already found when you are doing the retrieval step. So those same things could be reused in the generative step. And unfortunately, most people don't do that. Most people typically tend to think about retrieval and generation as two separate steps. You retrieve and you forget about query document correlations and document embeddings. You re-encode them when generating stuff, when generating the next tokens. Right? The third thing is unusually structured and sparse attention. So essentially, RAG is typically treated as standard LLM generation, paradigm, but RAG context typically has these block diagonal attention patterns where one document typically has, they typically have unusually structured and sparse attention. Okay. So therefore, these people propose a different architecture to do RAG. And the way it is done is as follows. It's a very simple idea, actually. Let us just go over it. So for this RAG, let's take this question. Who is the president of USA? That's basically the input query. And, you want to come up with an answer, Donald Trump, obviously, but you want to also figure out documents which support that answer so that you can actually retrieve relevant documents. Okay. So you take this query and then you basically pass it through a token encoder so as to token embeddings through a query encoder. And that basically gives you matches from the vector database, matching documents. So you have these matching documents. Okay. Now you take those documents and then what you do is to basically take those individual tokens, pass them through an encoder, the same encoder in that sense is, and then get a single chunk representation. So the idea is that you don't really use all of the tokens of these documents as part of your decoder foundational decoder model, I mean, typically, what do people do? Typically, people take the question, take these 3 documents that have been retrieved, and then you basically take these tokens, those tokens, concatenate them, and you essentially pass them through the decoders, generate the answer, Donald Trump. Okay. But what they are proposing is that rather than taking the entire document, you basically come up with a chunk embedding, and then you just pass those chunk embeddings to the decoder. So you see, these chunk embeddings are directly going to the decoder. So rather than actually passing, maybe like, 10 here, 10 here, 10 here, some 30 tokens, you just pass 3 tokens worth of information. So that is basically the change. So rather than passing the tokens of the documents individually to the decoder, you actually pass those chunk representations. However, in some cases, it might be super important to actually consider tokens of some chunks. So in some cases, you can actually pass token representations of these chunks, but in other cases, you might just pass one vector chunk embedding as such. Okay. So overall input, overall, the way it works is that you have the query, you get these matching documents, you basically get those documents, you take the token, you take the representations, pass them through encoder, get a chunk embedding, you project these chunk embeddings to the embedding space of the decoder. And then, for some of those chunk embeddings, some of those chunks, you just use the chunk embedding. For others, you basically use the token embeddings themselves. Okay. So the input typically looks like this. It basically comprises of the question tokens. Questions you basically use in a tokenized format, plus the context chunks. Some of those chunks may be represented using chunk embeddings. Others may be represented using token embeddings themselves. And then you basically pass it through the decoder, which generates the answer. Okay. In their work, they basically experiment with the LLaMA decoder and the Roberta encoder, but they also do some experiments with other kinds of decoder and encoder models. Okay. Now, how do they train their refrag model, right? So basically, they train, so it does need training, right? So you see, it does need training because there is this projection layer. So if you have a chunk embedding, you basically need to project, right? So as in the embedding space of the decoder, so it does need training. Also, it needs training to decide which chunks should be basically embedded using just one token versus, which chunks should be represented using their individual tokens themselves, okay? So they do this pre-training, and then they do supervised fine-tuning for specific downstream tasks. Okay, so for pre-training, they basically follow three principles as such, right? So the pre-training is done for reconstruction task. So and here the idea is not to do RAG. Remember, pre-training is not done using RAG kind of data. It's just done using standard, English sentences. So essentially, in fact, they call it the reconstruction task. So you give some input, and then you just do the next para prediction in that census. And remember, it's just using a decoder. So you freeze the decoder. In fact, for this task, the decoder is frozen and only train the encoder and projection layers. You see, I mean, essentially, you have the encoder here. So you take the chunk, you pass through the encoder, and essentially you have a projection layer and then the decoder, right? So you basically keep the decoder fixed, but you train the encoder and the projection layers such that decoder reconstructs the original info in a shifted format. So basically next para prediction. So you take the first chunk, try to predict the second chunk, take the second chunk, predict the third chunk, and so on. Okay, that's that. So while doing this, they do in a curriculum way. So what does curriculum way mean? Typically, curriculum learning means you basically incrementally increase the task difficulty. You start with simpler examples, and as you do more and more batches and more, as you do more and more steps, you basically increase the difficulty of the task. So therefore, they start with the simplest task where the encoder actually receives one chunk and the decoder tries to reconstruct k tokens corresponding to the next to one chunk, right, in that census. After that, they basically move to 2 chunks. So the encoder receives 2 chunks and the reconstruction is done for 2k tokens and so on. Okay. So where k is basically the chunk size. So if you, I mean, here essentially they decide the chunk size as well. So they can take the documents, divide them into k size chunks and so on. Okay. So that's that. So they do reconstruction, they do it in a curriculum learning way, and then they also do selective compression. As I was talking about, this thing is called selective compression, where for some chunks you compress and represent them using only one chunk embedding. For other chunks, you basically represent them using individual tokens themselves. Okay. So now how is this selective compression done? So I already talked about, what is selective compression? It basically means expanding important context chunks while representing not so important context chunks in as one embedding only. Okay. So they do that using RL. So they basically, or rather they train a model using RL. So what is the model? The model basically takes various chunk embeddings and tries to predict whether this chunk should be expanded or not. Okay, so basically it's super simple. Basically, for every chunk in the input, this model is going to basically take the entire concatenation of those chunks, and it's going to predict a logic for each of those chunks, say expand or not. Okay. Now to train this model, they train it in a RL manner, reinforcement learning manner, using GRPO reinforcement learning reinforcement learning algorithm, right? And the model is basically a two-layer transformer over chunk embeddings. It takes chunk embeddings as input and tries to predict, in the sequential order, and tries to predict for each chunk a logic which indicates whether to expand it or not. Okay. Now, this RL, the way the thing works, the way the model is trained is to do next paragraph prediction perplexity. So essentially, what you do is to basically take a training sample, right? And you try to figure out, let's say 20 different combinations where you have fixed certain percentage of chunks to be expanded. Let's say you have fixed like 20%, 5% chunks will be expanded, or 10% chunks will be expanded, right? So you figure out 20 different combinations of those 10 chunks that you'll be expanding, and everything else is not expanded. Okay. You give it to this a model, and or other, you basically take those expanded ones, you give it to the decoder model, figure out the perplexity that you get from that model, and that perplexity acts as a reward. Okay, so those combinations which lead to lower perplexity are preferred by the reinforcement learning algorithm. I mean, basically they're given a reward so as to prefer, those combinations where chunks. I mean, those combinations which led to lower perplexity. Right, that's that, and that is how you essentially use these rewards in the reinforcement learning algorithm so as to train this two-layer transformer network to predict, which chunks should be expanded or not. Now, given this, the encoder and decoder, while doing this, obviously, the encoder and decoder are fine-tuned to handle mixed inputs of compressed and non-compressed, uncompressed chunks. Okay. So that's basically their pre-training. Now, after this pre-training is done, you do supervised fine-tuning for various downstream tasks. They talk about two downstream tasks where transformer decoder models can make use of this logic, mainly RAG and multi-turn conversation. Multi-turn conversations also really require RAG, where the context basically is the conversational history, and also documents that can be retrieved for the current query using RAG from a larger document corpus. Okay. Okay, so how do these models perform? So, let's talk about the performance. So there's many plots and charts here. Let me talk one by one. So let's talk about this chart that you see here, right? So essentially here, there are three different subcharts here. Here, k equal to 16 is used. What does that mean? That means that the chunk size is fixed to 16, which basically means that you get 16x compression, 16 times compression in terms of the input by itself, right? What do you see? I mean, what are these plots for, right? So the plots here are for refrag cached, refrag not cached, and CEP. CEP is yet another method to actually, have efficient RAG in that sense, or efficient decoding. This has to do nothing with RAG, actually. This is basically standard plain decoding. So you give some input and you want some output. When you give the input, you basically want to just compress the input. Okay. So, and here, selective compression is done. Basically, you compress every chunk in that sense. Okay. So what do you observe here? So what is caching versus not caching? So refrag cached basically means that, you're going to use the embedding that has already been computed, while refrag not cached basically means that you're going to, recompute the embedding when you're going to do the generation in that senses. Okay. So, so here, what do you observe? You basically observe that as the number of input tokens are increasing, obviously, or rather, so there are three charts, right? So what are the three charts? So the first chart is for TTFT, time to first token. This is time to iterative token. This is throughput. Okay. Now, what you can observe is that compared to the plain vanilla RAG, right, or plain vanilla decoding, where the time to first token is going to be, is going to be proportional to the is going to be quadratic in terms of the input length, right? So what do you observe? That the acceleration, acceleration in terms of time to first token is much higher when you are doing refrag compared to another method called CEP, right? One thing to observe is that there is acceleration, which basically means that now you can actually process a very large amount of tokens very fast. 30 times compression, 30 times acceleration is what we're talking about, right? So this is 30 times acceleration in terms of time to first token. Similarly, 3 times acceleration in terms of time to iterative token, and 6 times throughput acceleration when it comes to really large context. Now, obviously, these methods are going to give you much better results when the context size is longer, is much larger, right? In that senses. Okay. So, but this plot is basically with k equal to 16, and here, there's no discussion about what is the quality that you get basically. And here there is no selective compression which is done. It's basically compress every chunk in that sense. Okay. But let's talk about more realistic scenarios now. So they basically also experimented with measuring perplexity for realistic data sets like archive and book, and also PG19 and proof pile and so on. I've shown some results here. Okay. So here what they did was to basically fix the input size to 2048 tokens. So that was the input size. Okay. And then they varied basically the output size, output number of tokens that would be output, right? Now, obviously, I mean, these are all decoder models. So if you give some input, they will generate the next paragraphs in that sense, right? So output size was fixed to 512 tokens, 1024 tokens, and 2048 tokens. Okay. Now, and then the perplexity was measured on the output. Okay. The perplexity was measured using a LLaMA 27 billion model. So that's that. So what you see here are perplexity numbers. And what you see are perplexity numbers for various models. So LLaMA full context basically means you passed the entire context. So 2048 sized context and asked it to generate 512 tokens, 1024 tokens, 2048 tokens, and so on. Okay. So LLaMA 32K basically means that you trimmed the LLaMA input, or rather, sorry, you use the LLaMA, which was basically trained on a 32K window. Okay, so LLaMA model in general, I think it has just 4K as the token length, but LLaMA 32K is a specialized version of LLaMA which has been trained on a 32K token length input. Okay. Then they also used LLaMA no context. Basically, this should perform poorly because you're not supplying any context at all and just asking it to generate stuff and measuring its perplexity. Right? LLaMA 256 is basically a specialized version of LLaMA where you basically chop off all the context of 2048 and just retain the last 256 tokens. Okay. Now this was basically done so that you can compare this LLaMA which takes 256 tokens with another model, for example, with let's say Refrag 8, because Refrag 8 also has 256 tokens. Refrag 8 basically means that you're setting k equal to 8, which basically means you're replacing 8 tokens by one chunk, one embedding. Okay, so they're like 2048 tokens. If you divide 8 8 to the 16. So basically it's like 256 tokens which are left with. And therefore Refrag 8 and LLaMA 256 actually have the same number of tokens as input. It's just that LLaMA 256 takes the last 256 tokens. Refrag 8 actually takes the entire input of 2048, divides it into 8 different, into 256 different parts, and then comes up with an embedding for each of those parts. Okay. So what do you observe? So and similarly, so replug and CEP are other efficient RAG techniques, basically, right? Or efficient decoding techniques in that sense. So what do you observe here? You observe that the perplexity is the lowest for refrag models, which basically shows that they work really well, right? Lower perplexity is better, obviously, right? Now, on the other hand, they also did other kind of experiments where you have the same methods, but you actually, and the same data sets, but you fix the output size and you change the input size. So they experimented with 4,000 tokens, 8,000 tokens, and they actually did for longer input context as well, right? And you can observe that LLaMA full context really goes really bad. That is those are the perplexities, and that happens because LLaMA model basically just has 4K as the 4K is the context length. So obviously, if you have a longer context length, it just suffers because it doesn't because the input just goes out of its it gets truncated significantly. Right, that's that. But refrag models actually still provide you the lowest perplexity. Okay. Now, this plot basically shows to you the compression rate versus perplexity when you are using a particular, selective compression policy. Okay, so remember, selective compression actually helps you decide which chunks should be compressed versus which chunks should not be compressed. Okay. So you can do this selection of chunks to be compressed in multiple ways. Obviously, you can use the reinforcement learning model that I talked about on the previous slide. That was basically learned using perplexity of the output tokens as a reward. Right? You could use that, or you could basically just take the chunks themselves, take the chunk text, pass it to a LLaMA model, a LLaMA 7 billion model, ask for the perplexity of just that chunk. And if the perplexity is lower, then you essentially, if the perplexity is lower, then you basically assume that it has very low information because the model really knows that information anyway, and therefore you compress it. But if the perplexity is higher, you don't compress it, right? That is basically a good way of also deciding, whether you should compress or not compress the chunk. Okay. So that's that. And so you can basically either compress low perplexity chunks or you can compress the high perplexity chunks. So those are the perplexity disk and perplexity ascending kind of methods. Yet another thing that you could do is to basically just just to random compression. So in the sense that you basically choose some chunks randomly to be compressed versus not. Okay. So x-axis is compression rate. So essentially, 1 in 4 chunks should be compressed, 1 in 8 chunks, 1 in 16 chunks, and so on. And what you observe is that your perplexity basically is the lowest with the blue curve, which is basically the reinforcement learning curve. So they basically say that, hey, although perplexity by definition could have been a very good way of doing this compression, but the reinforcement learning based method is a better way to figure out which chunks should be compressed versus not. Okay. Now they also experiment with RAG. So this is, all the experiments that I've talked about so far was just standard decoding, right? I mean, standard next paragraph prediction in that senses, but not really doing RAG. So, but they also experiment with RAG, where they vary the number of passages that are retrieved, and they try to check the performance of the question answering systems. Okay. So, blue one is standard LLaMA, and the orange one is Refrag. Now, Refrag is 8x compressed, and it also so as you can imagine, since it's 8x compressed, even if the input and you see the number of passages are basically kept the same, right? So essentially, so Refrag 8x compressed obviously will have 8 times smaller input length. Okay. What you observe is that typically the performance remains the same, which basically is super awesome because, with 8 times smaller input, you are retaining the performance of the original model of passing the original tokens themselves. Okay. But on the other hand, obviously it will have impact on the on basically the performance on the latency, right? So essentially, as you can see, the latency, if you basically see the orange curve, the orange curve is going to have much lower latency with much lower latency at the same performance. So for example, if you look at the blue curve, to get the score of about 52, it basically takes about 10 units of time versus this guy is going to take much smaller latency. It's much smaller units of time, right? So that's basically the benefit. I mean, you take much lower latency, but you get similar performance for RAG in this particular case. They also experiment with other kinds of scenarios like multi-turn dialogue modeling and so on. But for that, you can read up more in the paper. Okay. So in summary, Refrag is an interesting system which exploits the sparse and block diagonal attention patterns in RAG kind of contexts. It compresses those retrieved documents in form of chunks and comes up with just one embedding to represent the entire chunk rather than every token, right? It expands certain chunks if it senses that those chunks are important. Okay, so thereby it reduces the memory usage and inference latency. It is useful. This kind of a method is useful for RAG, for multi-turn conversations, long document summarization, and so on. And in general, they basically show about 31 times time to first token acceleration without any loss in perplexity or any downstream accuracy measurements. That's it for this video. Hope you liked the video. Thank you for watching. Connect with me on my LinkedIn or look at my research on my homepage. Thank you.